Hi everyone, this is a video walkthrough of problem 1, Oracle Dijkstra's on CS62NB, exam prep worksheet on MSTs, Dijkstra's, and tries. So let's dive in. In some graph G, we are given a sorted list of nodes sorted by their distances from some start vertex A. Design an efficient algorithm to find the shortest path tree starting from A. And our hint is our algorithm should be more efficient than Dijkstra's. Cool. So let's just kind of recall or recap. We are given a graph G, and we're also given a sorted list of nodes by distance to A. And what we want is the shortest path tree. Okay, so looking at this example graph on this right-hand side, let's quickly figure out what each of these three mean for this graph. Well, obviously, like this is the graph G. Okay, and then the sorted list of nodes that we would be given in this case would go B, because B is 1 away from A, then C, because C is 2 away, and then you'll have E, because E is 3 away, and then you'll have D. So that's for this case. And then what we want is the shortest path tree, which in this problem is going to look like so. Okay, so that's what we want, the shortest path tree. So how should we proceed? Well, what algorithm do we know finds the shortest path tree? Dijkstra's. But it says here that our algorithm should be more efficient than Dijkstra's, right? Well, how can we create an algorithm that's more efficient than Dijkstra's? By using Dijkstra's. It seems kind of weird. Well, let's kind of recall how Dijkstra's works, and then let's try to modify Dijkstra's, right? So our idea is, what if we can modify Dijkstra's to, I think I misspelled Dijkstra's, that's embarrassing, improve its runtime by leveraging the sorted list of nodes. Okay, so this is my idea. And in order to achieve this, let's first recall the algorithm for Dijkstra's. Okay, so this is just from lecture, and this is basically the algorithm for Dijkstra's. Okay, let's walk through it very quickly just so we understand what's happening. In Dijkstra's, what we do is we first add the source vertex with priority 0, and then for all the other vertices, we say that they're infinity away. Then what we do is iteratively, we keep taking the smallest person from the priority queue, then we relax all the edges from that person, okay? And then relaxing, all this really means is that we look at all the neighbors of a given vertex, and we ask ourselves, have we found a better path to any neighbor? Okay, so where would a sorted list of nodes maybe help reduce the runtime of Dijkstra's? Okay, so let's first remember what exactly constitutes the runtime of Dijkstra's, right? We know from lecture that the runtime of Dijkstra's is big O of E log V. And the reason Dijkstra's has this runtime is because the priority queue takes a while. Right? More precisely, in Dijkstra's, we have a lot of priority queue operations, right? We have to add to our priority queue. We have to change priority of vertices in the priority queue. And then we also have to remove vertices from the priority queue, okay? So I just want to recap why the runtime of Dijkstra's is E log V. It's because this change priority operation, potentially every edge we look at, we find a better way of getting to the vertex of that edge, right? So suppose that we have some edge, and then we're relaxing this edge in the relaxed subroutine. It's possible that this vertex V, we have now found a better path to get there. In that case, what we want to do is change the priority, so we call change priority. So potentially change priority can get called E times, where E is the number of edges, and each time it's called, how much work does it take? Well, since the priority queue has V vertices, and priority queue operations run in logarithmic time for change priority, the runtime becomes E log V for all of the change priority operations. And this is actually the most expensive operation in Dijkstra, and this is why we get this runtime. Okay, so long story short, what we want to do to improve our runtime of Dijkstra's, well, first what we could do is we can eliminate the change priority, right? But what if we can even take a bigger step and just eliminate all of these priority queue operations to begin with, right? Then what we can do is never have to touch the priority queue, and all we have to do in that case is just look at all of the vertices and all of the edges. So my idea is, what if we can remove the priority queue, and then the runtime is just iterating through the vertices and edges. So it would be the same as BFS or DFS, right? Well, in order to achieve that, we would have to get rid of all of these lines. Okay, so why can we potentially take this direction? Like, how could this possibly work? Well, let's kind of recall here that the only purpose of this priority queue is to tell us which vertex to look at next. This is very important, so I'm going to write that down again. So the priority queue purpose, which vertex to go to next. All right, that's the question the priority queue helps us solve. But now that we have a sorted list of nodes, we know the order of the vertices that we should be visiting, right? We know in this case, we want to go to B, then C, then E, and then D, right? So there's no real need to use a priority queue if we already know the ordering of these vertices, right? And how we should visit them. So the idea here is, let's kind of remove this code. Let me just kind of make it look like it was never there to begin with. Okay, and what we're going to do here instead is we're going to say that for each vertex P in the sorted list, relax all the edges from P. Okay, so that's the answer to the first problem of the exam prep worksheet. Just to recap, what we're going to do is we're going to remove the priority queue operations from the Dijkstra's, because the only purpose of the priority queue is to help us answer this question. And we know the answer to that question because of the sorted list of nodes, right? In Dijkstra's, we visit nodes based on their distance from the start. And since we're given this ordering, there's no point to create a priority queue to help us find it. Okay, because of this, what this implies is now our runtime is going to improve. More precisely, our runtime is going to be big O of E plus V. Since now all we're doing is, in essence, the equivalent of like a BFS or DFS, right? Okay, so that is all for this first problem. And yeah, stay tuned for problem 2.